Hello, this is Professor Kuehn. Welcome back to my lectures on electricity, magnetism, and light. We've been looking at Michael Faraday's experimental researches in electricity. You might recall in my last lecture, we talked about the first few experiments that Faraday had done. These were on page 303, 304, 305 in A Student's Guide Through the Great Physics Text, Volume 3. In those experiments, he described what he referred to by the end of that section as volta-electric induction. What does he mean by volta-electric induction? He means he was using a voltaic cell to produce an electrical current in one circuit, and that electrical current in one circuit was able to induce an electrical current in a second circuit that is completely separate from the first. He used, for example, two interpenetrating loops of wire and found that when one passes an electrical current through the first loop of wire, momentarily, an electrical current is generated in the second loop of wire. And it's only happened when the current in the primary or the first coil was turned on or when it was turned off. When there's a constant current flowing in the primary, there is no current in the secondary coil. So this seems to be a very curious effect. And now what he's going to do is explore this further. So that brings us to about page 305 in the section titled Evolution of Electricity from Magnetism. So the first thing that he's going to do is he's going to reproduce one of his earlier experiments, but instead of having two interpenetrating coils of wire that are wrapped around a common wooden dowel, he's going to wrap these coils independently around an iron ring. He gives the dimensions of the iron ring. He says it's 6 inches in external diameter, and he wrapped helices of copper wire that were 1/20th of an inch thick around both sides. If we were to jump ahead, we would see that the diagram figure 25.2 shows what this looks like. He has a coil of wire wrapped around at the side A of the welded ring, and those are hooked up to, as he says, a voltaic battery that he can turn on and off by connecting the wires. And the coil B, which is wrapped around the other half of the welded iron ring, is hooked up to a galvanometer. And then he notices that when he turns on or off the current in part A, or in coil A, suddenly there's a deflection, a large deflection of the galvanometer that's attached to coil B. He says in point 30, when the battery contact was made in one direction, the galvanometer needle was deflected on the one side. If made in the other direction, the deflection was on the other side. The deflection on making a battery contact always indicated an induced current in the opposite direction to that from the battery. But on breaking the contact, the deflection indicated an induced current in the same direction as that of the battery. So he's talking once again about how a current flowing through circuit A induces a current in circuit B, but only momentarily when there's a change in the current in coil A. And then he goes on to talk about, if we go to the next page, figure 25.3, he's talking about another arrangement. Well, actually, he hasn't gotten to figure 25.3 yet. Let's talk about first his point 34, where what he is doing is he is reproducing his previous experiment. Let me draw it over here to remind you. In the previous experiment, he took a wooden dowel and he wrapped these two coils around it. So I'll draw that. But he says now what's going to be different is I have this wooden dowel, but it's not a solid wooden dowel. It's a pasteboard cylinder, I think is what he called it. Think about like a paper towel roll. And he wraps these coils around it. So I'm going to draw a couple of coils wrapped around here. And again, one shouldn't take the number of coils that I'm drawing as indicative of the number of coils that he was using. So I'm drawing the primary and the secondary coils wrapped around here. And as before, one of them is hooked up to the galvanometer. So one can detect a current, and the other one is hooked up to a battery. So let's do that here. So these are hooked up to the terminals of a battery, and one can turn the battery on and off. And once again, he notices that when the battery current is turned on and off, the galvanometer momentarily deflects, but he notices that when he places an iron bar inside of this, an iron rod inside of this coil, the effect is greatly amplified. So the presence of an iron rod. And when he does this, it amplifies the effect that he had previously seen. So somehow this effect recruits whatever potential the iron rod has in order to amplify this effect. Okay, and now this leads him to an idea. He thinks about why the iron bar would have had an effect, and he decides, what if I get rid of the battery and the first coil altogether and simply magnetize and demagnetize the iron bar using magnets instead of electrical currents? Would that produce an electrical current flowing through the secondary coil into the galvanometer? And that's precisely what he does in figure 25.3. So you might imagine here, I'm gonna redraw it to sort of help clarify what's going on. So I'm gonna draw this iron bar like this, and imagine hooking up this coil around it, and this is hooked up to your galvanometer, which of course, as always, will deflect in one direction or the other if a current is induced in this. And if this is just an iron bar, so we have an iron bar right here, and an iron bar ordinarily is not magnetized. But let's suppose you take a couple of magnets, and I'm going to draw them like this. A couple of magnets, bar magnets, and you make them into kind of a V arrangement that you can snap together on and off of this iron bar. So this would be, by the way, the north end of this magnet, and this would be the north end of this magnet. This would be the south end of this magnet down here, and this would be the south end of this magnet here. So we have the marked pole, as he calls it. And he notices that when you snap these magnets together in such a way as to magnetize this iron bar, suddenly you get a large deflection of the galvanometer. But that action, that current through the galvanometer, quickly dies away. But then when you release the magnets, when you pull them apart, and what happens is you suddenly get a current in the opposite direction in the galvanometer. So this is explained in point 37. He says, upon making magnetic contact, the needle was deflected. Continuing the contact, the needle became indifferent, that is, it stopped indicating current, and resumed its first position. On breaking the contact, it was again deflected, but in the opposite direction to the first effect, and then it again became indifferent. When the magnetic contact was reversed, the deflections were also reversed. How does he understand this? So here he's finally succeeded in producing an electrical current simply using bar magnets, which is the goal that he had to begin with. How does he explain this phenomenon, or how does he describe it? That is depicted in figure 25.4. Here he's going to try to give a bit more precise description of the direction of the induced current in the galvanometer. And he says it in this way. He says, let's suppose you have this iron bar that is placed between the two poles of a horseshoe magnet, which is shown in figure 25.4. And let's suppose you were to wrap a coil around that bar, that iron bar. And here he only shows a single loop of that coil so as to simplify the drawing. And what he says is when you touch the iron bar, at that moment there's a current flowing through the wire that's generated in the direction shown. And the P and the N are to represent the positive and negative terminals of a battery that would drive the same current if you had a battery hooked up to that wire. So let me draw this to help explain this. So we have this horseshoe magnet like this. And suppose we take an iron bar and we touch it between the two faces of this horseshoe magnet. When you do this, the moment you touch it, suddenly there is a magnetic field or a magnetic directionality created in that direction, going from north to south. And at the moment that this contact is made, if you have this wire wrapped around like this, at that moment there's suddenly a current that is generated in this direction. So the creation of a magnetic field, so to speak, oriented as shown, that is from the marked pole, the marked north pole, to the unmarked pole, or unmarked south pole, generates momentarily an electrical current in the direction depicted. That is what he is saying in this diagram, figure 25.4. Now we are going to go on to explain this using various rules that came to be known as Lenz's law and Faraday's law. But what we see here are the actual experiments that Faraday carried out that inspired these laws to be enumerated. And so in the next lecture, what I want to do is talk more specifically about Lenz's law and Faraday's law, which capture the results that Faraday is describing in these experimental researches. Let me just say a couple of other things on this section before we move on. He talks about a few more experiments on the next page, kind of variations on these experiments. In section 44, he redoes the previous experiment with the horseshoe magnet and the iron bar, but instead of using a small horseshoe magnet, he uses an enormous magnet that was given to him by Dr. Kuehn Knight at the Royal Society, who had 450 bar magnets, each 15 inches long and 1 inch wide, and he sets it up as shown in figure 25.6. That's an end-on view looking at the north and south faces and the bar stretched across it, and he was able to generate a very large current upon making contact or upon disconnecting it. And then finally, on the next page, he talks about another attempt using an even more powerful magnet. That is by Professor at the Royal Institution, a magnet or lodestone belonging to Professor Daniel. It was by itself capable of lifting 30 pounds. And when he hooked up this iron bar, attached the iron bar to it with a coil wrapped around it, that coil generated enough current in it in order to powerfully convulse a frog. So here you have interesting results where they're trying to connect electrical currents generated by magnetic action to what was called then animal electricity. So if ever any of you have read Mary Shelley's Frankenstein, this is written around the same time during this Victorian era where people are trying to understand the connection between physical science and human life and animal life. And here you see the kinds of experiments that animated those kind of writing, so to speak. There's one other thing I'd like to point out is that on section 57, he talks about more experiments that are done in a similar way. And how were people measuring the electrical currents that were generated in these wires? Well, you might remember they were using galvanometers to measure them, but there were some other interesting ways that people were able to measure the electrical currents. First of all, by showing that a frog leg attached to them would suddenly jump. Another way that he mentions is by touching the wire to your tongue. And when you touch it to your tongue, you can feel it tingle. As it ends up, your tongue is a very sensitive measuring device for electrical currents. If you've ever perhaps licked the terminals of a battery, I don't recommend this, but if you do, you might feel a little tingle as the electrical current passes through your tongue. So he's doing these various experiments to sensitively detect electrical currents that are generated by these magnets. At the very end, in section 58, He says the similarity of action almost amounting to identity between common magnets and either electromagnets or volta-electric currents is strikingly in accordance with and confirmatory of Mr. Ampere's theory and furnishes powerful reasons for believing that the action is the same in both cases. But as a distinction in language is still necessary, I propose to call the agency thus exerted by ordinary magnets magnetoelectric or magnelectric induction. So he's trying to settle on some terms. We had been using volta-electric induction to refer to when you have a primary coil hooked up to a voltaic battery, and that induces a current in a secondary coil. Now he's saying, well, let's just call this a different kind of induction. So when you have a coil, a secondary coil wrapped around an iron bar and use a magnet to magnetize the iron bar, let's call that magnetoelectric induction. That way we have a way of talking about these various phenomena that he is discussing.